Hi everybody, this is Kathy Driscoll with the Nature Foundation at Wintergreen. I'm going to talk to you today about energy, and in particular, sound. So, what is energy is my very first question. If you were here, I would be answering lots of you guys, but I'm going to just have to pretend that you're saying it at your end. So, energy is actually something that has the capacity or ability to do work. So if I were to try to move something, I have the capacity to move something. That is energy. And there are different kinds of energy. So sound is one of our types of energies. And all of this that we're going to talk about today in science is mainly designed for 5th grade and understanding the different terminology that's involved with the sound energy. So different types of energy, I said, is sound. And I can just hear the energy from y'all's voice, where you're at, saying, oh gosh, Miss Kathy, there's other types of energy, such as light energy. And energy, we know, travels in waves, so we're going to just go over that. Light energy does. Sound energy, there's a thing called thermal energy and magnetic energy that is found in the natural world. Can we think of any other types of energy? Now, don't rush and say, I know all of them, but there are a couple more. Chemical energy. And with chemical energy, we can actually reflect back on understanding matter. If you have already discussed matter with your teacher in the classroom or with myself in the classroom, you probably have gone through the different phases of matter and doing some experiments with gases, liquids, and solids, okay? Putting two chemicals together, like a liquid chemical and a solid chemical, can create a new type of form of matter, but that chemical that we're talking about that created that was through energy, okay? So, the different types of energies, but today we're going to go into sound, and we're going to talk about how sound is transmitted and how it is received, and what types of media can sound energy travel through, and then also how it is produced, and lastly, how we use it, how we see this, how we feel this. So I need a little bit of help. I have my coworker, Sarah Leopard, from the University of Virginia, here to help us understand energy more.
Hi guys.
Hey! So one thing when we talk about sound energy and how it is transmitted, we refer to vibrations. So Sarah, I thought this would be kind of a neat demonstration if you can help me.
Sure.
So I tell you what, I'll have you hold it because I want you to just explain what you see or feel or hear. This is a gong, okay, and I'm going to hit the gong with my mallet, and Sarah is going to explain what she sees or feels or hears here. Ready?
So when you hit the gong, I heard a low vibrating noise, but I also felt the vibration through the string, so it traveled through the instrument.
Excellent. Very good. So we talked about sound being transmitted, and it's actually being transmitted with a vibration, through vibration, things moving back and forth. In fact, if we're doing it now, we're making sound.
Right, if you touch your voice box by your vocal cords, you can feel it vibrating as you speak.
Oh, yeah. So my vocal cords are transmitting the sound.
Right, and then your ear is receiving the sound that you transmit.
Oh, light bulb. Very good. Well, light's going to be another matter later. So we are creating sound, and with our vocal cords, we can also change the frequency and pitches of our voices. So we'll talk about that in a few minutes, because there's a couple of terms that we need to go over and understand first before we go into frequency and pitches. And how are we going to do that?
Well, first we're going to demonstrate with the Slinky. So hopefully you all are familiar with my favorite toy, the Slinky.
Slinky.
So I'm going to have Kathy hold one end, and then I'm going to ping it. And when I ping it, you're going to see a wave travel through the Slinky. So here I'm pinging it, and you can see it move throughout the Slinky. That is because it is sending a vibration. So this kind of wave that you can see after pinging it is called a compression, where it gets closer together at the beginning.
I noticed that it was going in one direction as well.
Right. It also, the vibration travels in one direction from this left to right. And so after the compression, you see
Like a stretch.
Yeah, you see it stretch out after it compresses.
Okay, so let's demonstrate that on the board here.
Right, we'll draw these.
Because when you talked about matter, you are actually talking about molecules that are found on, well, pretty much everywhere. But in matter, we refer to the atoms that create molecules, right? Well, here's a perfect example of where molecules come in and how they manage to move around, okay? So you said with the Slinky, first off, this is going to be our line. This is actually the resting state of energy. So this right here, when we talk about energy, is actually where we don't hear the sound. But I'm going to make the sound waves, okay, as the Slinky did. So here are our waves. And you talked about compressed. That means when Sarah pinged it, those waves got closer together, which means the molecules did what?
They compressed.
And they were hitting each other.
Right.
They got closer together, boom, and then they came away from each other. So that's called rarefaction,
Right.
where they go away. So this is called a compression of waves. Okay. Or longitudinal waves.
Right.
This is the line direction of traveling. And that would be measured either through distance or time.
Right.
Okay? So we said that all of these waves that came close together were compressed, molecules that hit each other. Oops, I'm saying and writing at the same time. Compression. And then when the molecules were bouncing off of each other and getting further away, the waves then became rarefaction. Okay, a couple of other terms you need to know about waves or sound waves. And that is the top of our compression wave is called a crest. And we also look at the distance between the waves. So let me do another one. Zoom like this. Okay. So the distance between each of these waves is called a
Wavelength.
yay! I heard them. I heard lots of voices going, Miss Kathy, that's wavelength. Everybody knows that. We can measure the wavelength. We can also measure the below the rest line is called a trough. Yeah, the amplitude is,
Let's fix that.
okay, amplitude is the distance from the top of the wavelength to the resting point where we said there was no sound, okay? And that is with a D. That is what we're going to work our way to, from transmitting to receiving. So let's talk about then the frequencies and pitches, and then we can get to amplitude.
Right, so frequency and pitch are also terms that you need to know. Frequency is the number of wavelengths. So the frequency can also define the speed of vibrations as you have a wave traveling. So a higher pitch means there's a higher speed that it is traveling at, whereas a lower pitch means it is slower. And then this is measured in hertz. So one way to talk about hertz is through what we humans can perceive. So humans can detect a frequency of 20 hertz at the minimum and then 20,000 at their maximum. So beyond this, we aren't able to hear these noises. So this is different than another animal. You might think of dogs that are able to sense prey. They have a much wider range of pitch. They can detect 47,000 to 65,000 hertz.
Wow, that's incredible.
It's a pretty big range.
I wish I could hear that well that nobody else could hear. Almost like, I don't know, the bionic woman. La. Or what other animal is capable of hearing and creating pitches or frequencies that we can't hear?
Well, bats are a good example. I don't know if you've heard of echolocation, but that is how bats send waves out, and then that is beyond what the human ear can hear without the use of technology. But luckily, we have our baton or bat box. So a bat box can detect at a frequency that bats are transmitting. So if you move your fingers over it, it is detecting the movement.
So that's kind of like the bat actually sending out a frequency when it goes that we don't hear, but the baton can pick it up.
Exactly.
And the baton can actually pick it up when the frequency is faster and when it's slower.
Exactly.
That is too cool. All right, let's talk about that, and we're going to talk about the amplitude. One thing that is important to discuss is like our speaker, because our speakers definitely they amplify sound for us. So I actually have this, whoopsie, I turned it off. Let me see if you can hear this wave. Would you get me on your wavelength now? So I could crank up the sound or the amplification, or bring it down. So that vibration that we were talking about is actually going through a speaker and providing or transmitting the sound so that we can receive it, whether it's going to be loud or soft. Which, by the way, this is Wavelength, the song. Okay, so let's talk about then amplification as far as how forceful a wave is made. Okay, and one of the things that we can demonstrate this with, and with amplification, it too can be measured just like the pitch or the frequency is measured in hertz, but amplitude can be measured in what we call decibels. Okay,
Right.
so how many decibels is your human ear allowed to hear? Okay, this is important because sometimes if you are inundated, in other words, you're getting a lot of noise at a long period of time, your ear, which actually has like a tympanum, a screen-like structure that bounces and it vibrates to pick up the noise, it can actually be damaged with high decibels. So if you crank up the music too loud, you can damage your hearing. Okay, and but that's not going to happen with this because I have a ukulele and it's not that very loud. But this kind of gives us an idea of the movement. So we talked about transmission, or moving in waves and the vibration, and then the different pitches. So if I play my ukulele this way, if I put my finger across one of the frets and I hold down all of the strings, then the pitch is going to be different. It's almost a little higher.
Right, so the higher pitch would mean that it's traveling faster.
Even though my finger is. There you go, bling. Next time I'll teach you some song on ukulele.
Love performance.
All right, so, but how can we, see this or understand this a little more? So I actually have my phone with an app, and Sarah's going to kind of zoom in on this. This is a great way to see how our sound waves can travel, and it is called an oscope. So if you see here, there is our wavelengths going along here, and as I'm talking, you see that the waves get really tall, and if I talk really low, then the waves are much smaller. It is measuring the hertz, and it's measuring the amplification here. So if I get really, really loud, or my pitch gets high, or low, high, the waves are really tight together, they're moving fast, low, low, I'm trying to get low, low. The waves are further apart, they're moving slower, okay? So another way to measure amplification